Yeah. So this was the problem we gave yesterday. So did we complete this problem?
Yes, sir.
Hmm. So we
Yes,
will
sir.
do some more problems today. So this was the problem we did, and we did some interesting problems with different types of sources, and we also saw how the circuit elements are also given for different types of problems. Either they could be in the given in the form directly in the form of the circuit elements, or they can be given in the form of the reactances and resistances. And sometimes we saw that they are also given just in this problem, like they're given in the form of uh, mm, conductance and susceptance. So you have to be very careful when as you are given the numerical to see how the circuit elements are given, and also regarding these units. You see in this problem everything is given in milliampere, millisiemens. So again that has to be taken care. Okay, you have to watch them, and since it is AC, I have been telling repeatedly that you will have to consider the phasors, because the phasors actually reveal many things. It may even lead you, help you to, you know, prevent you to make mistakes also. It will actually help you if you are going in the wrong direction and all, because everything has to be represented in the form of a phasor. So we saw this example where you are given the two currents I1 and I2, and you are asked to find out the values of the voltages V1 and V2. And what we did was we took help of the nodal analysis. And so at these two nodes we wrote down the at these two nodes we wrote down the the KCL equations, and ultimately we solved them. So we saw that in these solutions, the unknowns are actually complex quantities, and they have to be solved, and ultimately you get this type of, again, the complex quantities. So we learned about this way of representation in the form of magnitude and the phase, and ultimately you get the solution in the form of magnitude and phase, and then again it has to be represented in the phasor diagram. Okay, so that is the V1 and V2. So V1 and V2, it is not just the magnitude, you have to also detail the angle where that phasor is, and also similarly for V2. So this is the thing that is going to come now again and again, because we are right now in AC, and in AC any physical quantity has to be represented in the form of phasor, obviously to some proper scale. Okay, also like the currents are one type of physical quantity. For currents you can use one scale, for voltages you can use another scale, and draw it in the phasor diagram. So this problem we completed. Let us do some another problem today. Uh, so this is application of the Thevenin's theorem in the AC. So determine the Thevenin equivalent seen by the minus 10 ohm impedance. Okay, so this is the circuit where you are asked to find out the Thevenin equivalent across the minus 10 ohm impedance. Okay, and you find these to use this to find the value of the voltage V1. Okay, so the circuit is given to you. So you are asked to find the Thevenin equivalent. So Thevenin equivalent means what? Finding what? The Thevenin voltage,
Thevenin
Voltage and
resistance.
VTH and
Voltage and
RTH.
voltage and
VTH,
resistance.
okay, so VTH and RTH, so everything you have to do by
Excuse
removing
me,
that
sir.
impedance. Yes,
Sir, can we apply Thevenin across like capacitors and inductors as well?
this is the thing we are doing. I have given it to you the circuit where where you find that the circuit elements are associated with J. J means there is a capacitor or an inductor. If it is plus J, there is a inductor. If it is minus J, there is a capacitor.
Okay, sir.
So the question here is to find out the Thevenin equivalent across the minus J 10 ohms. minus J10 ohms, and so first draw the circuits for this. Huh? Yeah. So find out the.
6.12.
So basically, these are the two things to be found out for Thevenin equivalent. It is VTH, the Thevenin voltage, and it is, in this case, it will be called ZTH because the Thevenin impedance. Okay, so we all know that to find this, you basically have two circuits. So to find VTH, what you have to do? Remove that impedance. Remove that impedance and find out the voltage across the two open terminals. Finding out the voltage across the open terminal. Similarly, to find out ZTH or the Thevenin impedance, what you have to do is across those two open terminals, you will have to find the impedance, but by de-energizing or deactivating the sources. If it is a current source, they have to be
Open.
open circuited, and if it is a voltage source, they have to be shorted.
Short circuited.
So some sort of a
Okay.
some sort of this type of thing you have to do. So draw the circuits for the two cases here.
So there is 6 plus 2J.
So 8 minus 4J.
So first is the Thevenin voltage, and then is the Thevenin impedance. How much is the Thevenin impedance?
6 plus 2J.
6 plus 2J, sir.
6 plus 2J. You can visualize Thevenin impedance. So basically, this is the
The root
circuit.
40.
To find out the Thevenin voltage, you basically have this circuit. I have removed the minus J10 ohm impedance and kept the circuit as it is. And now it is required to find out what is the voltage across the two open terminals. Similarly, for the Thevenin impedance, this is the circuit. Across those two terminals, what is the impedance? By deactivating the sources. Now in this case, it was a current source, so as soon as you deactivate, basically means that circuit is gone. That part of the wires are should not be considered to exist. Okay, so you are basically left with this circuit. So you can find out the ZTH basically orally.
Sir, VTH is equal to 2.236 angle minus 26.56.
Angle.
Sir, VTH 6.7 angle 22.5 minus.
Tell me in the A plus JB form.
26.56.
Tell me in the A plus
6
JB
minus
form.
3J.
So
6 minus 3J.
8 minus 4J.
8
No.
minus
Sir,
4J.
VTH equal to 6 minus
Sir,
3J.
8 minus
RTH
4J, sir.
plus 2J.
So 6 minus 3J. So 6
6
minus
minus
3J.
3J.
6 minus 3J.
Sir, 6 minus 3J.
Yes, sir. 6 minus
Hmm.
3J.
Yes,
And then
sir.
then you tell me what is the value of V1.
Sir, 6 V1.
4 minus
Sir,
2J.
4 minus 2J.
4
4 minus 2J.
4 minus 2J.
5 minus 2J.
4 minus 2J.
So 4 minus 2J.
4 minus 2J.
And V And V2 equal to 2 minus J.
VTH equals to 2 minus J.
VTH 2 minus J. 2 minus J, no.
6
Sir,
minus
8
3J.
minus
6 minus 3J.
6 minus
Yes, sir,
3J.
6 minus 3J.
Hmm.
Yes, sir.
Yes, sir, 6 minus.
So find out VTH. Like, so VTH is equal to the
6.708.
you have to basically find out.
0.7.
So it is basically the potential difference between the point 1 and point 2.
V1,
Okay,
V2.
so you have to find the potential at point 1. So if this is current is 1 angle 0, you can find out what is the potential at point 1. Similarly, with the current 0.5 minus 90 in this direction, what is the potential at point 2? And these two phase differences is going to give you the VTH. So at point 1, this is the voltage. At point 1, at terminal 1, this is the voltage. And and from this you have to basically subtract the potential at point 2. So that is the VTH that has been asked. So basically it is minus of this. So this minus means, suppose this we reverse this current, so it becomes minus 0.5 angle of minus 90 multiplied by 2 plus J4. So that potential has to be subtracted from, so that is the potential at point 2. So you subtract it from the potential at point 1 and get the VTH. Okay.
Sir, why
Yes.
did that negative sign come? Please explain.
Which one?
So minus.
And because the current is going out in that direction, the 0.5 angle minus
Direction of
90.
current.
So if I just reverse that current, so it will become minus. I reverse that current because I want to find the potential at point 2. So I reverse that current, so it become minus. So that is the total potential at point 2. Minus 0.5 angle minus 90 into 2 plus J4.
Yes, sir.
1 to get VTH. Okay.
Yes, sir.
So after doing this multiplication, you will get something like this.
Yes, sir.
Yes, sir.
And so that is the VTH. You check my complex multiplication additions are correct or not. If there is a mistake, please tell me.
Yes, sir, it is correct.
Yes, sir.
I am
Correct.
getting the same answer only.
Correct.
So
No, not getting the same answer. We both of us can also make mistakes. So just tell me whether my correction is calculations are correct. You know.
Yes, sir.
So
Correct.
that is VTH. Similarly, ZTH. You know that it will be very easy. It can be done orally because they are in series. So ZTH
Yes, sir.
is
6
equal
plus
to 6 plus 2J.
6 plus 2J.
Okay, so you have found out the VTH and ZTH. So when for a circuit, to find the Thevenin equivalent, we have seen that basically first that impedance has to be removed, and then across those two branches finding out the Thevenin equivalent, and Thevenin equivalence, it is the voltage as well as the impedance. And once you get these Thevenin equivalents, you can again you can find out what is the current through that load resistance, load impedance in this case. So again you can reconstruct the circuit like this. So now you have got this VTH, okay, 6 minus J3, and the RTH and the ZTH in this case is 6 plus J2, and across the terminal 1 and 2. So that was the Thevenin equivalent found out across the terminal 1 and 2. So if you replace back the load impedance across 1 and 2, it is again minus J10. Okay. So here now what you can do? You can find out what is the current in the circuit. You can find out what is the current in the circuit. And the next part of the question is use this to find the value of V1. That is the voltage at the terminal 1. Okay, so find out the voltage.
Is it 1 minus 2j?
Sir, V1 is equal to 4.472 minus 26.56.
So 4 minus 2j.
Yes, sir.
4 minus
Yes, sir. 4 minus 2J.
Sir, it's 4 minus
minus
2j.
2j.
Sir, it's 4 minus 2j. Yes, sir.
Yes, sir.
So what is the current? Current from 1 to 2. That is I12. That is current from 1 to 2. Will be
Sir,
what?
6 minus 3J. 6 minus
That is
3J
the-
divided by 6.
Divided by 6 plus 2j minus 10j.
Yes, sir.
Okay. So find out this current.
0.6 plus 0.3j.
0.6 plus j 0.3j. So this is the current. So this is the current flowing through the this is the current flowing through in the circuit. So the potential at point 1 you should be able to find out. That is the voltage across the J10 ohm impedance. Okay, so I1, that is the current in this. There was also one question asked that what is the current in I1? So I1 is basically V1 by so I1 is basically the current, that is the total current minus the current flowing through the J10 ohm. Okay, you see
Yes,
that
sir.
current, the total current, that is 1 angle 0 minus the current flowing from terminal 1 to terminal 2, which you have just found out is 0.6J. Now once you know I1, you can find out what is V1. Looking into the circuit, once you know I1 is flowing through 4 minus J2, you can find out the V1.
Sir, what was the value of
Sir,
V1?
1 minus 2J. 1 minus 2J.
Okay,
1
so
minus
this
2J.
is your I1. Okay, I angle, the 1 angle 0 is basically 1 plus J0. That is 1 minus 0.6 minus J3 minus J0.3. And so your I1 is this. And now once you have got I1, you should be able to find out V1. Okay, so
1
V1 is
minus 2j.
4
Sir, 1
minus,
minus 2J.
1 minus 2j.
1 minus 2.
1
this
minus
is-
2J.
okay, 1 minus J2. Okay, and obviously in this slide, because of space, I could not draw. You should be able to represent the phasors. Okay, you should be able to represent the phasors. But just by seeing at the complex values, you should be able to know that that where in which quadrant the phasors will be. Okay, suppose
Sir?
I.
So can we write VTH minus V1 equals to 6 plus 2j times current?
VTH.
VTH minus V1 equals to current times 6 plus 2j.
No,
I,
then we will take V2 to be 0. That will lead to incorrect answer. V2 is not 0. We have assumed reference as different in initial condition.
okay, so the phasor diagram also has to be accompanied along with the something is given. So whatever is given, you can draw the phasors quickly, and then whatever the unknowns are found out also needs to be represented in the phasors. Okay. So we have done some numericals, and a lot of numericals are there in the books. The references we have given, and basically the tutorial sheet 2 that you are going to do also will have the numericals on these topics. But tutorial sheet will have some 8 or 10 questions, but it is better a tutorial sheet anyway you have to do, but to get a more exhaustive practice, you have to follow some book or say from multiple books to work out the numericals. Yes.
Sir. So when will we get the tutorial sheet 2, sir?
Tutorial sheet 2 will be given on the day of the tutorial.
Sir, can you not give this before 1 day, sir? Please.
Yes, sir.
So
No,
actually,
you
we
sir,
can
please provide
so
1 day
we can
prior than the tutorial day.
Huh?
Sir,
so
we
we
can
can
try on a day
go-
before and ask if we have some doubt on the tutorial
Yes,
day.
sir.
No,
Yes,
no,
sir,
the
yes,
purpose
sir.
of the tutorial is, tutorial is also like one sort of an exam, So when you are here, in the even the actual offline tutorial that we take in the classrooms, you have to solve it on that day only
Yes,
in
sir.
our presence.
Okay, sir.
So the odd numbered questions you will do in our presence, and even numbered you will have to submit like an assignment. So that is the purpose of the tutorial. So for practice, you can practice from so many books I have given. If you want real practice, so the purpose of the tutorial is you have to practice from several places and come for the tutorial. Okay,
There is solution of Hayat and Kimadli available.
that you check. I don't know.
These exercises don't contain the answers.
Okay, so we have practiced some 4-5 numericals on AC circuits. So we will do something else today. So there is something called resonance, there is a phenomenon called resonance which is observed in AC circuits. So here what we have is basically an RLC circuit in the form of a series. There is a series RLC circuit supplied by an alternating source. Okay, and the values of directly the circuit values are given, and so since in an AC circuit it gives rise to impedance, so we also need to provide that omega or the supply frequency. So we know that this V, the supply voltage, is equal to VR plus VL plus VC, but this plus or this addition is not just direct addition, it is the the addition of the phasor. Yes, so the addition of the phasors, and ultimately we get the impedance of the circuit in this form: R plus J omega L plus 1 by J omega C. So that is the total impedance of the circuit. So this is series RLC. We know this, L, the reactance part is J omega L. For C, the reactance part is 1 by J omega C. And then since it is a series, you just add them to get the series impedance. So this thing, if you, the J is basically root over of -1, so J square is -1. So you know how we got this, how we took the J in the numerator, and it basically results in a minus J in the capacitor part. So you get R plus J omega L minus J by omega C. So the total impedance is of this form. So R plus J omega L minus 1 by omega C. Okay, so there is a real part and there is a imaginary part to the impedance. So this can be represented in the form of a magnitude of the impedance, that is mod Z with a certain angle. So you know how the angle is. So mod Z is basically the square root of the square of the resistance plus omega L minus 1 by omega C whole square. Similarly, this theta is basically equal to the tan inverse of omega L minus 1 by omega C divided by R. So that is how we get the theta. So that is how we get the magnitude and angle of the impedance. Okay, so in all this, what is essential is we have to be provided the value of omega. Just giving the circuit element values is not sufficient. The value of omega has to be given, and once omega is given, omega is also obtained once the supply frequency is known, and as we told that the supply frequency depends upon the system, or the country has a fixed supply frequency from where you can find the omega. You can also find out this. So for a particular circuit, you can find out the theta. Now, this XL, that is this omega L, that is the reactance that is offered by the inductor, is denoted by XL. The reactance symbol is X. Okay, so this is so XL, that is the reactance value offered by the inductor, is XL is equal to omega L. Similarly, XC, that is the magnitude of the reactance offered by the capacitor, is 1, which is given by Xc is equal to 1 by omega C. So so if you plot this, okay, if you plot the reactances, okay, so so you see the reactance is basically, whether it is an inductive reactance or the capacitive reactance, it is basically a function of what? Omega, because your L and C are fixed. Okay, so XL equal to omega L, how will it look like?
Y equal to omega.
Linear line.
It will be a straight line. Okay,
Passing through origin.
so if your XL equal to omega L, X equal to 1 by omega C, so your Z becomes R plus J XL minus XC. Okay, R plus J XL minus. So you see here that how we have defined XC. We have XC we have defined as 1 by omega C. XC we have defined as 1 by omega C. So inside the bracket it is XL minus XC. So if we plot this now, if you plot XL in the X omega plane, you see the plane is X and omega. So in the Y axis it is the reactance and X axis is omega. So it will basically look something like this. Okay, so in the XL omega plane it will basically look something like this. And now if I plot minus XC, how will it look like?
Rectangular hyperbola.
Hyperbola.
Minus XC at omega equal to 0, what is the value of XC? Infinity.
Minus infinity.
Minus infinity. Okay, so it will be looking like something like this. So and as omega increases, what is the value as omega increases?
Value decreases.
XC decreasing.
Decreasing, but in the negative side,
Increasing.
Increasing.
Yes, sir.
The value is increasing.
Negative sense it is
Because
increasing.
it is negative and mod is decreasing.
So value is tending to 0.
tending to 0. Okay, so but in which quadrant it is?
Fourth quadrant.
Fourth
So
quadrant.
it will be in the fourth quadrant.
Fourth.
Okay, so
Fourth
it will increase something like this. Okay, if we plot this minus XC, it will plot something. Why are we plotting minus XC? Because in that bracket it is XL minus XC. Okay, so it is basically XL plus of minus XC. So you see, ultimately XL minus XC or XL plus of minus XC. So that is the total reactance offered by a circuit consisting of L and C. So you see, for low values of omega, what is happening? Which one is dominant? The low value of omega?
Capacitance.
The capacitance is dominant. Okay, and
Capacitor.
if you see for higher values of omega,
Inductor is
inductor is dominant.
Inductor.
Okay, so in the lower omega region range, the capacitor is dominant. In the higher omega region, the inductor is dominant. And one is positive, the other is negative. There will be some region where they will exactly cancel each other, and there will be a certain frequency or omega where they will exactly cancel each other. Okay, at a certain frequency they will exactly cancel each other. The magnitude of the positive part and the magnitude of the negative part is exactly same. So if they exactly cancel each other, what happens at that time?
Resonance, sir.
Resonance will occur.
It is only resistive. And it will only resistive.
Only resistive circuit.
The circuit is purely resistive because the reactance part is gone. Okay, the inductive reactance cancels the reactive capacitive reactance, and is known as the resonant frequency or omega r. So at a particular frequency, both the reactive inductance and the capacitive inductance cancels each other, and the net circuit is basically it is so at that omega r. So if the supply frequency is omega r, the circuit is a purely resistive circuit. The circuit becomes purely resistive. Okay, so you can find out what omega r it basically happens. So Z is minimum. You see the magnitude of Z. If omega L and omega C cancels, so this part is gone. The Z is minimum when your omega L minus 1 by omega C is equal to 0. Okay, so the reactive impedance part is 0 at the resonant frequency, and that is the point where the value of Z is minimum, and it is just only due to the resistance. Okay, so this omega R is basically given by 1 by root over of LC. The resonant frequency is given by 1 by root over of LC, which is known as the resonant frequency. Okay.
Yes, sir.
Yes, sir.
Yes, sir.
So now let us see what happens at that frequency. So this is a frequency that can happen because if your this supply frequency, if somehow you can make this omega that is the frequency to be a variable quantity, then there will be at a particular frequency this thing will happen, and the reactive component of the impedance becomes 0, and so that frequency is known as the resonant frequency. So that will basically depend upon the values of L and C. So if you are given a certain L and C, you can find out using that L and C what will be the resonant frequency.
Excuse me, sir. Sir, but in practical, if we see, then omega is dependent on the like the omega of the generator. No? So how can we vary that? Because our electricity is coming from the source, that is the generator.
No, that is a very good question. What is who to ask this question?
Sir, Rugved.
Raghuveer?
Sir, Rugved.
Okay, anyway, Rugved. So that is a very good question. So once you are in a particular system, the frequency is fixed. But in also many of you will be doing experiments in the laboratory. There are actually function generators where the frequency can be varied. Okay, and so in many of these electronic experiments, we will basically do this.
Sir, so we can also manage L and C, sir. We can also manage L and C to get omega R.
So, so that also will be the reverse way. If you have to achieve a certain omega R, then you manage L and C. If you have to achieve certain omega R, then you to achieve that omega R, what will be the L and C? That may be required in a particular work, particular application. But as somebody asked, how to get this? So there are function generators in the laboratory where it is possible to change the frequency. So by changing the frequency, you can see that the total impedance of the circuit is also gradually changing. So as the impedance change, all the other circuit quantities also change. That can be done in the labs. Okay.
Okay, sir.
So now your current is basically given by V by Z. Okay, this is AC circuit. We are just going to use the word Z. So V by Z, which is given by V by R plus J omega L minus 1 by omega C, and then this is if you just consider the magnitude. So this is the magnitude of the current. Okay, so this is the magnitude of the current, and we just saw that since this whole impedance is in the denominator, so if your omega L minus 1 by omega C part goes, so that results in the minimum value of the denominator, so that will actually result in the maximum value of the current. Okay, so that will basically result. So if as your omega is changing, the point where omega L just cancels 1 by minus 1 by omega C, the denominator is minimum. If the denominator is minimum, the current is maximum. Okay, so if you plot this, so if you plot the current or the absolute value of the current, if you plot the absolute value of the current along with the frequency, okay, so the current, the absolute value or the magnitude of the current will actually change with frequency. Okay, and there will be a certain omega where it will be maximum and less at other values of omega. Okay, so the absolute value of current with frequency will actually look something like this. Okay, for lower values, okay, there will be certain impedance, so that will result in a lower value of the current. Similarly for the higher values of omega, but there will be a certain omega in between where this omega L exactly cancels minus 1 by omega C, and there the current is actually the maximum. Okay, so that is the maximum current, and it is achieved at a particular frequency, which is omega R. Which is achieved at a particular frequency, which is omega R. So this frequency, so resonant frequency is the frequency where the reactive impedance vanishes. Obviously, it has to be an RLC circuit. There has to be L as well as C, because one is going to cancel the other. If you just have RL, it will not happen. The L effect and the C effect, they cancel each other, and this is the net value of the impedance is just the resistance, and at that time you get the maximum current. Okay. Now, if you look into the phase, there is a phase offered by the impedance. It is Z equal to R plus JX. Okay, and X is again a combination of omega L and minus 1 by omega C. So at lower values of omega, what was dominant?
Capacitance.
Capacitance was dominant. So capacitance, if there is a capacitance is dominant, what is
Current is leading.
the
It will
angle?
start from minus 90
Current will
degree.
lead
Minus
positive.
Current will lead.
Minus 90.
It will start from minus 90 degree and then go to plus 90 degree.
Current will
If
lead. sir.
And plus 90 to minus 2.
It will be plus 90
Yes,
to
sir,
minus
current
90.
will lead.
current will lead, because in the lower value,
So not audible.
So your voice is cutting.
voice is cutting. I don't know. I have done nothing. I have done no change. I apart from
it
this.
has capacitive nature.
So if the capacitive nature, what happens to the angle?
So the
Plus
angle.
Sir, angle
current
current
is,
minus 90, sir.
The angle is positive, plus 90.
Plus
Okay.
90.
So for lower value, suppose that omega equal to 0, the whole impedance is due to the inductance is gone. It is totally capacitive. So it will be starting from plus 90, and as the omega increases, what happens? The capacitive value reduces. We saw in the in this graph we saw as the omega increases, the capacitive reduces, and the reactive the impedance due to the L inductor increases. Increases.
Hello,
in that
sir.
case,
Sir, here phase angle is theta, na sir? Tan inverse omega L minus 1 by omega C divided by R. So sir, when omega will be 0, then it will be tan inverse minus infinity, na sir?
Yes, sir. And then it will be
Then
minus.
it will give minus 90 angle. Sir.
Minus 90 degree.
but minus 90 it is in the denominator. So if you take V by that, so when you
No,
take
sir,
it to
I'm saying about theta, sir. Theta.
Ah.
Theta is
So you
theta
are
is
plotting
tan
phase
inverse.
angle versus omega.
that
Yes,
theta,
sir, theta.
what I am talking is about the theta of the current.
Oh, okay, sir. Okay, sir. I'm impedance. I was saying.
The impedance is in the denominator. If you take to the numerator, it becomes positive. Okay, so your phase angle will basically look something like this. And exactly at omega r, there is no phase angle because it is a purely resistive circuit. Okay?
Yes, sir.
Sir.
Okay, sir.
So you see that towards the lower values of the frequency, since the capacitive effect is dominant and current is leading the voltage, so it is the leading condition. Okay, the current is leading the voltage. So that happens during the lower values of the frequency. Similarly, at higher values, the current lags the voltage because the inductor effect is dominant. Okay?
Hello, sir. Sir, what are the applications of resonance?
Applications of resonance, you can there may be a circuit way to find out where the current is maximum, at what frequency. So that will actually happen at a particular frequency. So it may also happen. It may also happen
Sir,
that
in many systems, sir, the measurement is near the resonance is because the response is very reactive near the resonance.
No,
We can
that
measure
may also
small
happen,
changes.
but since at resonance the current is maximum, sometimes in actual circuits, it may be required to avoid the resonance, because if that point
sir.
the circuit, the current is maximum, so it may lead to some other problem. Okay, so it may be required that if the frequency is changing, and so you don't keep it in the resonant condition for too long, because in that case there will be high value of current and it may lead to other problems. Okay, so you may try to avoid the resonance condition.
Sir,
Because in a
small-
resonance, yeah.
Sir, just I have a doubt that if the R means the resistive impedance is removed from the circuit, and then if the omega is adjusted such that the denominator will tend to zero, what is the means physical significance of that? Means will the current tend to infinity? Means what's
No, what you are telling, R is also zero.
Yeah.
As soon as you have wires, there will be R. Okay, so
Sir, it's talking about LC circuit, sir.
Yes.
No, even in
Yes,
LC, ultimately to make the circuit, you will have resistance. Okay, so there will be some R.
Sir, for the ideal case?
Ideal case, then it is all mathematics. Okay, so whatever happens in mathematics, you will have infinite current and all. Then, so that is what mathematics tells us.
Okay, sir.
Okay, so what happens at resonance is, so what is the value of the voltage in the capacitor? What is the current in during the at resonance? V by R.
Yes, sir.
Okay, so the what is the voltage across the capacitor? V by R into XC, because XC is the what?
1 upon omega.
Yeah, whatever it is. So XC is the reactance offered by the capacitance. So which is nothing but equal to 1 by omega C. Okay, so 1 by omega C, and since we are talking of resonance, it is omega RC. So it is 1 by omega RC into V. So this part the coefficient of V, 1 by omega r CR, we can represent it by some factor which is called Q. Okay, so the absolute value of the capacitor voltage is basically equal to QV. So this Q is basically called the quality factor of the circuit.
Yes, sir.
Quality factor or the Q factor of the circuit. Okay, so this 1 by omega RCR is called the quality factor of the circuit. So your Q is equal to 1 by omega RCR, and omega we found out as 1 by root over LC. If you substitute this, you can find out the value of the
root L by C, sir.
root over L by C. So that L by C is under the root
Into 1 by R.
Into 1 by R.
Sir, root over L by C into 1 by R, there should be
1 by R or L by R?
Yes, sir.
1 by R.
1 by R.
1 by R. 1
Sir,
by
1 by R.
1 by R.
Sorry. Yes, it is 1 by R. You saw this? Q is equal to root over L by C multiplied by 1 by R.
Yes, sir.
So that is the quality factor
Yes,
of the
sir.
circuit. And so now there is another new term which is called the bandwidth. Okay, so bandwidth is defined as the frequency range between the half point or half power points. That is the points where the power is half the maximum power possible. Okay, so the maximum power is possible where the current is
At resonance.
current is Imax. Okay, so the
Current
maximum
is maximum.
Yeah, so the current is maximum. The max is how much? V by R.
Sir, it
Okay,
will be V by R.
V by R. So the power max is P max, which is equal to V square by R. Yeah,
V square into V square by R.
V square by R. So if you substitute this, so the half power is basically means is where the power is exactly half of the maximum
V square
power.
by 2R.
Okay.
V square by 2R.
So when does it happen?
Sir, I did not understand the half point, sir.
Huh?
What means of
The half-
P?
P half means where the power is exactly half the maximum possible power.
Okay, sir.
Okay, because this is a circuit where we just now saw that if you vary omega, there will be different values of current. You see from the top, so as the value of omega changes, so there will be maximum power at I max. So where is at which value of current it will be exactly the half of the maximum power. Obviously, it will.
I by root. Sir, at
RMS value.
So it will happen at a certain value of current, and so
I by root 2.
So that we are trying to find out. So P max, so P half equal to half P max equal to 1 by 2 V square by R equal to 1 by 2. I max is basically V by R, so it is I max square R is equal to I max by root 2 whole square R. Okay, so from this we see that the half power basically occurs at the value of the current where it is I max by root 2. Okay, so where is it? So I max by so this I max is 1 by root 2 is basically 0.707. So where the current is 0.707 I max, you basically have power. So 0.0707 I max is obviously less than the max, and that will again occur at, that will not occur at a particular frequency. That will basically occur at two values of the frequency. Because as soon as you cut the current curve at 0.707 I max, you see that basically occurs at two values of the frequency. Okay. So between these two values of the frequency, so at these two values of the frequency, the power is exactly half the maximum possible power. Okay, so it basically happens at two values of the frequency, the lower frequency being omega 1 and the upper frequency being omega 2. So here it basically the half of the power occurs.
Sir, you are not audible.
I am not speaking.
Sir,
Now I
in
am
bandwidth do we excuse me, sir.
Hmm.
In bandwidth, do we have to use frequency and omega like 2 pi f, that formula, or is it omega only?
Whichever you have to use the correct units. If it is f, the unit is hertz. If it is omega, the unit is radians per second.
Okay, sir.
Your unit will tell what you are using. Okay, so the job is to find out these omega 1 and omega 2. Okay, these omega 1 and omega 2 where the half power occurs. Okay, the job is to find out the values of omega 1 and omega 2. And if you know the omega 1 and omega 2, one is lower and the other is higher, you can even find out the difference. And all these things you can do. So that is basically the bandwidth. The bandwidth is defined as the frequency range between which the half power, between the half power points. So if the shape of this current versus omega changes, if that blue curve changes, that frequency range will also change. So the blue curve will change for different circuit components. Okay. So at half power, what actually happens is the mod z, that is the absolute value of the so at half power, what actually happens is this, it basically occurs at I max by root 2. Half power occurs at I max by root 2. So in that case, what is the impedance? Impedance is equal to mod z is equal to V by I max by root 2. And this is equal to root 2 V by I max. So V by I max is what?
R.
R, yes, sir.
So at half power, the absolute value of the impedance is equal to root over 2R. So root over 2R means what? What is the expression of impedance?
R square plus root
R
under
R square plus J omega L minus 1 by omega C whole
Omega
square.
L minus 1 by.
So when will it become root 2R?
when omega L minus 1 by omega C is R.
Yeah, so
45 to
that will happen only. So this is your Z. And so at half power, your omega L minus 1 by omega C is equal to R. The half power will occur when omega L minus omega C equal to R. So earlier we saw that for resonance, omega L minus 1 by omega C equal to 0. But half power will occur when that reactance part is exactly equal to the resistance. And how many values will be there for omega?
Sir, there will be two values.
Two values, sir.
Two values.
Yeah, so find out those two values.
So the difference of those two values is R by L.
R by L, yes.
Sir, I calculated.
Yes, difference.
Two values is?
The difference is R by L.
Sir, it is R by 12 plus or minus root
The
or R
term is
square
R by L.
1 by LC.
Yeah, so it will be in many things it can be expressed. I want you to express the two frequencies omega 1 and omega 2 in terms of omega r, resonant frequency, and the quality factor q. Give me the value of omega 1 and omega 2 in terms
Sir,
of
omega 1 is equals to minus RC plus under root R square C square plus 4LC divided by 2LC.
No, I want you to give it in terms of the quality factor q and the resonant frequency r, omega r.
Okay, sir.
Omega 1 is equal to omega r plus omega r by 2q, and omega 2 is equal to omega r minus omega r by 2q.
I have taken omega 1 to be lower one. Okay. So and
Omega 2 minus omega 1 is equal to omega naught by q.
Find out. Give me omega 2 and omega 1 in terms of the resonant frequency omega r and the quality factor. Just I will give you 1 minute or maybe 2 minutes to do this.
Sir, omega 2 is omega r.
Yes, sir. I have got, sir.
1 plus q by 2 whole brackets.
Sir. Sir.
Yes, sir. I got the same.
Hello.
Sir, I got omega r by 2q into 1 plus minus root over of 4q square plus 1.
Sir, omega 2 is equal to omega r by 2q plus root over omega r square by 4l square plus 1 by omega r square.
Hello, sir.
Hello.
So who has found out omega 2, omega 1?
Sir, omega r 2q into 1
omega
plus
r
minus
by
square root
plus
of
or
4q
minus
square
root over
plus 1.
omega r square plus 1 by omega square.
So solving for this omega for that half power frequencies. So omega 2 equal to, are you getting this? I told you to express in terms of the resonant frequency and the quality factor.
Yes, sir.
Yes, sir.
Yes, sir.
Okay, and okay, obviously one has to be higher.
Yes, sir. Yes,
so
sir.
then
Yes,
the
sir.
omega 2 to be the higher, and omega 1. Okay.
Sir, no, sir.
Huh?
It will be plus
plus minus.
You write
plus,
so the minus will
plus
be
minus,
first term will be
over of
same
term.
for both.
Yes.
Sign will be plus minus.
Sir, minus will be in the root over.
The
Sir,
first term will
quality
be same for and
definition.
the sign will be plus minus in between.
Which one?
So both omega 1 and omega 2 are equal. One have minus sign.
No, sir, it's okay. There is minus sign first.
You see, I have kept the minus sign. I have to. How can they be both equal? You know.
Yes, sir. Yes.
Yes, sir. Got it, sir.
It is a quadratic equation, and it will have two different solutions. Okay, so we are now looking for the bandwidth, which is omega 2 minus omega 1.
Both
So this is
roads
So
omega r by q.
R by L.
So omega r by q. So what is omega r? So it is basically equal to the resonant frequency by the quality factor. The resonant frequency by the quality factor. So that is how we get the bandwidth.
Sir, why both roots are same? Oh, sorry, minus is there.
Okay, so now see all these phenomena, the bandwidth we actually will depend upon the nature of the curve. Okay, then and that will again depend upon the value of L and C inside the LRC of the value.
So sine of omega r upon 2q should be same in both omega 1 and omega 2. Sine of omega r into under root 1 plus 1 by 4q square should be opposite, plus and minus.
No, it is
So no,
correct.
it is correct. Otherwise, omega 1 will be negative.
No, it's all right. It's all
Actually, the
right.
mistake is omega L minus 1 by omega C mod should be equal to R. From there, we will get 4 solutions of omega. Out of that, 2 will be not possible and 2 will be these two
Yes, sir.
solutions.
Yes.
Yes, sir. Otherwise, omega 1 will become negative if we
We will
do
get
the
actually
opposite.
4 solutions out of which 2 is not possible.
Yeah.
So if we plot this, this omega again plot the magnitude of the current versus omega, so we can get these type of curves. But all these curves will actually depend upon the values of the circuit elements. Okay, the different types of the curve can be flat, the curve can be very peaky, and there can be curves in between. Okay, so this will actually result in different types of bandwidths. So circuits are, the circuits that are having very narrow bandwidth, that means the difference between this omega 2 and omega 1 is very small. These are known as the highly selective circuits.
Q value is very high.
Quality factor will be high for those circuits.
Okay, so that is the concept of resonance. Since we are doing AC, these are the different phenomena which are observed in AC circuits, and then we'll have to handle them. Now the next topic is the power in AC circuits, AC power.
Sorry, can you please show the previous slide?
Sir, what do we mean by selective circuits?
They are very narrow circuits, that half power occurs very quickly, that within a very short range. That half power situation.
Bandwidth is very small.
Yes.
Very small.
Thank you, sir.
Now, suppose we have a RL circuit. So we know that suppose if you apply Vt equal to Vm cos omega t, then it will give rise to some It, where It value you can find out It equal to Vm by root over of omega r square plus omega square L square. So that is the Im, that is the magnitude of the current, and it will be obviously cos omega t plus phi, because RL circuit, the current and the voltage will never be together. There will be a phase angle between them. So here this Im is basically given by Vm, the magnitude of the voltage divided by r square root of r square plus omega square L square, and the angle, that is that phi, is given by minus of tan inverse of omega L by r. Okay, so this thing we already studied, and we can also draw the phasor diagram and all. Now, since in an AC circuit, the voltages and currents are all functions of time. Okay, they are at every instant of time. If there is a certain voltage, then there is a corresponding current. Since the voltage is varying, the current also varies, and we just see in front of us the voltage and current expressions, and if we plot them in a graph, we can see their the nature. Both are having sinusoidal nature, and but obviously due to phi, there will be a phase shift between voltage and current, and obviously there will be a difference in magnitude. Okay, voltage and current will have different magnitudes, but the nature is basically the sinusoidal nature. And at every t there is a Vt and there is an It. So at every instant we can actually find out what is the power. Voltage is Vt and the corresponding current is It. Then the power at that instant Pt is given by Vt into It. So if we substitute the Vt and It, so Vt is equal to Vm cos omega t, It is equal to Im cos omega t plus phi. So this is equal to Vm Im cos omega t plus phi. The product of two cos will be equal to sum of two cos or sine.
Two
Huh?
Two cos.
So what will it be?
2 cos.
Vm Im cos omega t cos omega t plus phi.
Cos of a minus b plus cos of a plus b.
Plus cos
so-
omega t.
First divide by 2 into multiply by 2 and then we have to break.
So what is this? Cos omega t cos c
Cos 2 omega t plus 5 plus cos 5.
cos of 2 omega t plus 5 plus cos phi. Yes. So divided by 2.
Yes, by 2.
Divided by 2. Okay. So it will be Vm Im by 2 cos phi plus Vm Im by 2 cos 2 omega t plus phi. Okay. So you see the voltages and currents. What was the frequency of voltage and current? The frequency was omega. But you see for the power, it is varying with a component that is having twice omega. Okay, there is a constant part, and there is a part that is also sinusoidally changing, but with twice the frequency. Okay, so in alternating in AC systems, no, the power is varying is also sinusoidal. Since we are assumed the voltage and then we got the current also sinusoidal, now we see that the power is also sinusoidal. And obviously we are talking of instantaneous power, that power at a particular instant. And if you plot them at every instant, you see that the power is also a sinusoidal in nature, but it is having twice the frequency as the voltage and current. So if you plot it, you will be basically getting something like this. So you see here, what I have shown is that in the red is the voltage and the blue one is the current. Okay, so the voltage and the current, they are both sinusoidal, but the current is reduced in magnitude as well as shifted in phase. The current is reduced in magnitude, but it is shifted in phase, and we have plotted it in the same graph. So we see that there is a shift. But see the power. By the power. So if you consider the voltage as one cycle of the voltage, you see in that one cycle of the voltage, the power has basically covered two cycles. Okay, in one cycle of the voltage, the power is basically covered two cycles. So that is due to the 2 omega t component that is appearing in the power expression. Okay, so it just comes directly from the mathematics that the power is changing at twice the rate as the voltages and currents. Okay.
Yes, sir.
So,
Yes.
so here the phase of power and phase of voltage you are taken same.
Phase of power and voltage, and I have not taken same. It has come by itself. Whenever you apply a voltage, the current is at a certain phase.
In the graph, both are at same point. Power and voltage.
Power
and voltage.
Power is if you see the power has got shifted up. Okay. Power and voltage, the peak to peak values are not within the same range. Power is shifted up because of the Vm Im by 2 cos phi. There is a bias, positive bias added to the power. Okay. For the power, the baseline is somewhere else. Okay.
Yes, sir.
So we have, in our all other AC quantities so far we have studied, we have studied about the average value, we have studied about the RMS value and all those things. Okay, so if you recollect, so the average value, we know this, if there is a sinusoidally varying quantity, the average value from 0 to pi to 2 pi, then this is how it is defined. It is 1 by the 2 pi, then integration that quantity with respect to the time and over the whole interval. And in that case, in this case, what will be the value?
0, sir.
0.
0. Okay, because it is a sinusoidally varying, the positive half cancels exactly the negative half, and ultimately, if you do the averaging over the whole cycle, the value is 0. So, what is the solution? So, we do over half of the cycle.
Half cycle.
Okay, so similarly for the power, if you do for the power, find out the power average value of the power over half of the cycle. So that PT, if we do from 0 to pi, PT we do from 0 to pi.
For cos
Sir,
2
sir,
omega
for
t
power,
for
we
full
can.
cycle.
Sir,
Huh?
So for power, it's still full cycle because it's
yes,
moving
sir,
at
we can
right
define
moving
power
cos 2
by
omega t.
full cycle
Huh.
because it is not linear, sir. It is a square of a current and voltage.
Square.
Yes, sir.
It is a product of.
Product.
Sir, we can define average in full cycle, sir,
Huh.
for power.
So the omega t component will be 0, but the first component will be there.
Yes,
Yeah.
sir.
So what is the value of the power?
So the cos phi will be there.
So the expression is Vm Im by 2 cos phi. Okay, so that is the average value of the power. Even if you do over the full cycle, so this is basically the constant part. Vm Im is known by 2 and cos phi, which are none of them are actually varying with time. Okay, so this is the part that will remain. So there is the average power Vm Im by 2 cos phi. So in general, for the power over any two different time intervals, if you are asked to find out the average power, so it is 1 by T2 minus T1 integration T1 to T2 Pt dt.
Sir,
Okay.
why you have written in the P average term d omega t?
Omega t is the angle, na?
Because
Omega t is the angle.
Limit is changed here. So sir.
Okay.
So you have to master all these average values, RMS values. They will be there in the tutorial sheet too. You can also get similar exercises in the books. So if you are given some arbitrary waveform, how to compute the average values or the RMS values by the definition we have defined. So now suppose you have a network like this. Okay, and if we feed some voltage Vm cos omega t plus theta, arbitrary alternately changing voltage quantity Vm cos omega t plus theta. So obviously you know how to represent it. This is basically the voltage phasor is at a certain angle theta with respect to the reference. So if this type of voltage is fed to the network, which I have represented just in the form of a black box, it will actually lead to a current like this Im cos omega t plus phi. Okay, so where is your current phasor? The current phasor will be at a certain angle.
Phi above
at a certain angle phi, and in that case, In our case, suppose let us assume this phi is less than theta, so it is somewhere here. Okay, so this is basically happening to the current phasor, and obviously current and the voltage phasors are of different magnitude. Ideally, Vm and Im will be different. Okay, now there is basically some angle between the voltage and current phasors theta minus phi. So that is the angle by which we tell that how much is IT lagging Vt, how much is the current lagging the voltage, which is given by theta minus phi. Okay, so early many of the problems we were showing that the current phasor is aligned to the reference or voltage phasor is aligned to the reference. In that case, it is very easy to calculate those angles and all. But if it is at certain voltage phasor at a certain angle theta and the current phasor at a certain angle phi, then basically the relative difference between them is theta minus phi. What happened? So this theta minus phi, why have we done this? Because you see, this theta minus this angle is this is the angle that matters. So we assume that Vt equal to Vm cos omega t, It equal to Im cos omega t plus phi. So this phi, that is the relative phase difference between the voltage and the current phasors, is actually appearing in the average power expression. So we saw that the average power is equal to Vm Im by 2 cos phi in that case. But if the angle between them is theta minus phi, it will be basically the theta minus phi. So that is the thing we are going to do here. So the relative angle is theta minus phi. So in that case, the average power is Vm Im by 2 cos of theta minus phi. And now if it is a pure resistor, okay, so if it is a pure resistor, what happens to theta and phi?
Same.
Both are same.
Sir, zero. Zero.
Theta minus
So
phi
the
equal
phase
to
angle
0.
will be 0 and cos 0 equal to 1.
Zero.
So theta and phi both are the same. Okay, so theta minus phi is equal to 0. So in that case, the average power is Vm Im by 2.
Maximum.
Okay, Vm Im by 2. Now you see the difference. This is an AC circuit. We are doing AC. It is the average power is Vm Im by 2. Okay, if it is not a DC, where you will just multiply the voltage and current. So here we are talking of average power because both of them are changing with time, and the average power is Vm Im by 2. Now, suppose if you are using a pure inductor or a pure capacitor, if you are
Zero.
using a
Power equal to zero, sir. The average zero.
Power 0, sir.
so what happens? The voltage and current
phi equal to 9.
So in a pure inductor or capacitor, what happens? The voltage and the current phasors are orthogonal. They are perpendicular to each other.
Yes.
So theta minus phi is either plus or minus 90 degree. Okay, so theta minus phi is either plus or minus 90 degree. And then what happens to cos 90?
Zero.
So
Zero. Okay, so the P average power is 0. So the average power stored in an inductor or capacitor in an AC circuit is basically 0. So for a pure inductor or capacitor, the voltage and currents are perpendicular, and the difference between the angles is 90 degree plus minus 90 degree, and you get the average power as 0.
Sir?
Hmm.
Hello, sir. But sir, in pure inductor or capacitor, when there will be resonance, then it will be no resistance. So what will be that case?
This is this case, na? In a pure inductor or capacitor, where just a hypothetical situation we are talking, where even there is not at all any resistance, the angle is either plus 90 degree or minus 90 degree. What is the doubt? Hmm?
No, sir. Actually, I got it, sir.
Yeah. So you see this AC for an AC system. This is the average value of power Vm Im by 2 cos theta minus phi. That is which is the relative angle between the voltage and current. And these are the ideal cases when the pure resistor or pure inductor or capacitor, which generally will not happen, but just for theoretical sense, just for the sake of mathematics, this will be the situation. So this is basically the concept of the power in AC circuits. We'll do more on power. But we have just introduced the power, the concept of instantaneous power, and as well, because both the voltage and current are a function of time, and as soon as there is instantaneous power, we have also the concept of average power and so on.
Hello, sir.
Ah.
Sir, like in DC circuits, in AC circuits also the sources absorb power.
The sources here, the sources are delivering power.
No, in DC circuit there are some cases when the battery gets charged.
Yes.
So,
Yes.
Okay, so the next thing that we will do, and I think that is the last thing we will do today, is just like in in DC, you also have the maximum power transfer theorem in alternating current. And suppose you have a circuit like this where the source is an alternating source, that is the Vs, and supply. So obviously the source will have its own impedance, Rs plus Jxs, the impedance, the source impedance. And then there is the load. The load is, as I've been telling repeatedly, the load is the customer, the load is the user. Okay, in your all of us as the load, because we consume the electrical power, whether it is for the domestic use or in our departments or in our hostels, we are all loads because we are consuming power. And every time we are switching on and off the power. Sometimes you are switching on the television, sometimes you are switching on the refrigerator, sometimes you are charging your mobile, or sometimes charging your laptop. So all of them are loads, and sometimes you switch them off also. So the load is basically varying quantity, and as the load varies, the source keeps on supplying, but the source has to supply. Okay, whether it is a thermal power station or a nuclear power station or some hydel station, that has to keep on supplying. And the source, which is basically a generator, which will have its own resistance and reactance. Okay, because there is a lot of coil inside this generator. So the source impedance is basically Rs plus Jxs, and it is delivering to the load, which is always varying. Okay, because we are always varying. We have a different consumption pattern. Even if you consider yourself as a consumer and you just see your consumption throughout the day. Okay, at whatever you consume at 8 a.m., it will be different from whatever you consume at 10 a.m., but it will be different from whatever you consume at 6 p.m. and so on. If you just see in your own house, there are different consumptions. You in the evening you switch on the lights and the other lighting items, which are again not working in the daytime. Okay, your refrigerator may be working around the clock. Okay, your TV may be there only in the evening. So basically what is happening, your load is changing. So for that reason, I have kept that bar sign with an arrow on the load as basically a variable quantity. Okay, when you do your experiments, you will find the circuits where this type of arrow is given. That actually means variable resistance or variable reactance. And in your labs, you will actually handle that type of variable things, like in the form of a rheostat and all. So if your load is a variable, basically both RL and XL are variable. Okay, so RL and XL are variable, so that is the impedance, load impedance ZL. And so the current in the circuit is given by Vs by, you can just find out, the real parts will get added, Rs plus RL and J XS plus XL. And if you consider its absolute value, it is basically like this. Okay, the absolute value of the current is Vs by root over of Rs plus RL whole square plus XL XS plus XL whole square. Now, what is the power consumed by the load? The power consumed by the load is basically I square RL, because the load is consuming power and the load is only due to the resistive element. So the power consumed by the load is I square RL. Whatever is the I square times the RL is actually the power consumed by the load. And if you substitute this, so this is equal to, it leads to this expression. Okay, so now you
Only
see
the
this.
resistance consume the power.
Huh?
Only the resistance will consume power.
Yes. The real power, the actual power is due to the only the resistance. If you are using a, suppose you are using a room heater. Okay, if you are using a room heater, you get all that heat. It is basically the I square R. Okay, so now in this expression of power, what are the variables?
So RL and XL.
RL and XL.
RL and XL.
Okay, so RL and XL are the variables. Okay, so all of us are engineers, all of us has done some mathematics. So you will obviously try to find out, okay, when this power is maximized. RL and XL are variables, but RS and XS are fixed. Okay, with respect to that fixed values, at what situation the maximum power is consumed by the load. So you will find out what? You will find out the value of the derivative of the power with respect to RL. Similarly, you can also find out the derivative of the power with respect to XL.
So since there are two variables, shouldn't we actually do partial derivatives here?
Yeah, it is partial derivative only. When you are doing with respect to RL, XL is constant. Yeah, so maybe that symbol is.
Okay, sir.
And finding the derivative and equating it to 0. So what will the first one lead to? Find out.
Sir, why partial derivative with respect to XL is also 0?
Then when you do with respect to XL, you assume RL to be constant.
No, why it is 0?
Because XL is also a variable.
Okay.
In the load, as I am telling you the examples, you just consider your own.
But you said that only RL is responsible for the power consumption.
Yeah, but in the power expression, there how many variables are there?
Yeah, got it.
Sir, RL is coming minus RS plus root RS square minus 1 by 2.
Resistance is coming to be negative.
No, sir, minus RS plus root RS square minus 1, root of RS square minus 1 by 2.
Sir, RL is coming.
I am getting
equal
RL
to
equals to
Sir, RL
RS
equal to
and
root
XL is
RS
coming
square.
equal to
XS is
minus
minus
XL.
XL.
RL equals to minus. XL is minus XL.
RS.
RL is RS.
You check this derivative. You should be very much confident to do this type of derivative.
So from these two derivatives, the second, we will get two equations, and from one of the equations, we'll get the value of XL, and if we put the value in the first one, we'll get the value of RL. That is how I have done, and I got RL equal to RS and XL equal to X minus XS.
Anyway, so ultimately, I am not going to teach derivatives here. Okay, ultimately, you will get something like this. Okay, so that will become 0 when your RL is equal to RS. So that derivative, there is a numerator, there is a denominator. You'll have to do the numerator by denominator form. And ultimately, equating to 0, you will get RL equal to RS. Similarly, for XL, you will get XL equal to minus XSS. Minus XS. Okay,
Minus
so
XS.
yeah, so the power consumed is maximum when your load impedance is basically equal to RS minus J of XS. Okay, RS minus J of XS. What is your source impedance?
RS plus J of X.
J of XS. So what does it mean?
This
So
is the conjugate of that.
Conjugate of this. So when your load impedance is the conjugate of the source impedance, then you will get the maximum power. The maximum power is consumed by the load. Okay. Complex conjugate. So we are doing AC. There will be a source impedance. Source means the generator. Not just the generator, all the connecting wires. So generators and the connecting wires together is the source impedance. So when that impedance, when the load impedance becomes exactly equal to the complex conjugate of the source impedance, we get the maximum power from maximum power is consumed by the load. Okay, so that is basically the maximum power transfer theorem, which you can write down in the form of a statement. So in the case of DC, we saw that maximum power consumed when the source resistance is equal to the load resistance. But in the AC case, in the case of AC, we just see it actually comes out of this derivation. Although I have not shown the derivative and all, you should do the derivative yourself. It actually comes out that when the load resistance is a complex conjugate of the source impedance, then there is the maximum power.
Sir, we can tell that it is the conjugate of its Thevenin's resistance.
Yes, you can tell many things. Yeah, if it is in some numerical, if it turns out to be the Thevenin impedance and the Thevenin voltage given, then if the load impedance is the conjugate of the Thevenin impedance, it draws maximum power.
In this case, the circuit will be in resonance. The circuit will be in resonance.
Why?
Because XC and XL are cancelled out. Only the circuit remains is resistive.
Resistive, but the resistance gets doubled.
Yes, sir.
Okay, so it is something different because the reactance parts cancel each other, but the resistance gets doubled.
So, but in this case, the current and the voltage will be in the same phase then.
And the angle between them will be 0.
So that may happen. That is obviously it becomes a purely resistive circuit. And obviously that is the purely resistive as well as the minimum possible impedance.
Okay, sir.
Okay. So this is maximum power transfer theorem, very important theorem, just like your DC, and you will get also numericals related to that. But the only difference you have to remember, and this derivation you should do on your own, which I have not shown here, all the derivation and equating to 0 and getting this condition. It is a simple derivation and it should not lead to any complex expressions or something like that. So the maximum power is derived in case of an AC when the load impedance is the complex conjugate of the source impedance. So that is you can write down the statement, or you get the statements in the books. Now we have got this situation where if you are given a network that you feed the voltage Vm equal to cos omega t plus theta, and so this is the phasor is located at an angle theta, and you get a current Im cos omega t plus phi. The phasor is located at phi. Okay, and the relative angle between them is theta minus phi. Then we saw that the average power is Vm Im by 2 cos theta minus phi. Vm Im by 2 cos theta minus phi. So we can write it like this: Vm by root 2 Im by root 2 cos theta minus phi. So what is Vm by root 2?
VRMS.
Yeah, so it is Vrms, or sometimes we call this V effective, the effective voltage. Similarly, Im by root 2, because both of them are sinusoidal in nature. Okay, so that is basically their effective values. So it basically leads to V effective I effective cos theta minus phi. Okay, so V effective I effective cos theta minus phi. Now this V effective I effective, if you multiply these, just the effective values, there is a sinusoidal input Vm cos omega t plus theta. You are getting a sinusoidal outcome Im cos omega t plus phi. So then just the product of their effective values is known as the apparent power. Just the product of their effective values. The product of their effective values is known as apparent power. So what you get is cos theta minus phi is basically apparent power by the average power by the apparent power. So cos theta minus phi is known as average power by apparent power. Okay, and this theta minus phi is basically a property due to the circuit elements. This theta minus phi will basically occur due to the circuit elements. Okay, it will be totally dictated by the circuit parameters. So this is basically called the power factor of the circuit. The theta minus phi, cos theta minus phi, which is defined as the ratio of the average power by apparent power, is known as the power factor of the circuit, or in the books you will find in the abbreviated form as called PF. Okay, so cos theta minus phi is, that is, first you find out the angle between the voltage and current phasor and take its cos. So that is known as the power factor of the circuit, which is defined as the ratio of the average power by apparent power. A lot of times, I'm asked for a definition, and just somebody just tells cos theta or cos of the angle between, but it is defined as the ratio of the average power by apparent power. Okay. So this theta minus phi is basically the angle between the Vt and It, and if your theta is greater than phi, so the circuit is basically inductive, because the voltage is ahead of the current. Inductive, and if your theta is less than phi, the it's capacitive. Okay. But what happens to cos?
The cost remains the same because negative
Remains same.
the remaining
Cos remains same because cos of minus theta is
cos
cos theta. Okay, cos of minus theta is cos theta. Okay, so theta greater than phi inductive, the power factor cos theta is a certain value, but theta minus phi, if your phi is greater, but still cos phi is always positive. Okay, so this cos of this angle, so to find the angle, basically you have to do, so if your power factor is given, so to get the angle between the voltage and current phasors, you basically have to find out the cos inverse. Okay, so to get the angle, you have to do cos inverse. And then whether it is the condition, whether it is given leading or lagging, you will have to place the voltage and the current phasors. If it is told it is an inductive circuit with a particular power factor, you can find the cos inverse to find the angle, and then you can draw the voltage and current phasors. Because it is inductive, current will lag the voltage. But if it is told the power factor is given and it is a leading circuit, you can find the angle by taking the cos inverse and then place the phasors, and your current phasor will be ahead of the voltage phasor.
Sir,
Hmm.
sir, average power can also be negative. So what will it signify?
Where is it negative?
Sir, because of cos theta present.
Cos theta can be negative.
No.
Cos theta minus phi.
So he's saying maybe if theta minus phi becomes greater
Yes, sir,
than
is
pi by
greater
2,
than 90 degree.
but it does
No,
not become greater
but
than
phase is
that.
always minus 90 to
Never
plus
become
90.
greater than
Yes,
90
sir.
degrees. But
Yes,
It
Yes,
does
sir,
not become
understood.
greater
Understood.
than that.
Yes, sir, understood.
Okay. So this is the concept of power factor, okay, which is defined as the ratio of the average power and apparent power. Okay, so we will stop here today, and from the next day we will start with more discussion on power and some more analysis. More discussion is power is pending. So just to introduce the concept of power factor, we will end here today. Thank you.
Thank you, sir.
Thank you.